What I want to do now is actually to consider some problems, some example problems, really this time using the second approximation. Okay, so look, we'll have a look at the problem we've just really considered here. And all right, what do we have? We had a 10-volt source sitting here. Okay, we then had a 10K resistor, and then we had our diode. Okay, there is our diode. All right, now you were asked basically to find, in the previous problem, the current ID and also the voltage VD. All right, so here's my current ID. But this time I'm going to use the second approximation. Okay, so look, let's define that voltage there, plus minus again, as the voltage VD. So what we're going to do now is we're simply going to basically take a loop. All right, so as we go around the loop, all right, let's see, before we start, if ID is flowing in this direction, let's be consistent with our defined polarity. ID flowing this way, we would have a polarity across that resistor of plus minus. All right, we're ready. Okay, let's take the loop, start here. Okay, I come to the source. I'm going from a minus to a plus, that's 10 volts. Okay, from a plus to a minus, that is a minus. ID times 10K. Continuing round the loop, I have now my plus to a minus, that's a minus VD, all equals 0. Okay? All right, now since we're using the second approximation, and we'll assume here it's a silicon diode, okay, the voltage VD is equal to 0.7 once the diode is conducting. And of course, this voltage source is in such a direction as to put that diode into a forward bias mode and therefore conducting. So we'll put this 0.7 then into our loop equation and we'll start collecting our terms together. Okay, so what have we got? We've got 10 minus ID times 10K minus VD, which is 0.7, all equals 0. Okay, so we can collect these two terms together over here. All right, so that's 10 minus 0.7, and if I take this term over to the other side, that's this term here to the other side, this becomes equals ID times 10K. All right, so 10 minus 0.7 is what? 9.3. If I divide both sides by 10K, there's the 10K, that would be equal to my ID. And so therefore ID then is equal to 9.3 divided by 10K, which is 0.93 milliamps. Okay? All right, so very easy to work that problem if we're using the second approximation. All right, let's consider another example. Okay. Slightly more involved. All right, so the circuit that we'll now deal with is this one. Okay, we've got a 10-volt source here. Okay, we've got our silicon diode, so we'll say this is a silicon diode here. This is connected to another diode, which we'll say is a germanium diode. And we've got a resistor here, which is 1K, and that now is the circuit we wish to deal with, okay? And our task is really to find, if you like, the voltage VO, which is across that 1K resistor. Now, once again, as with so many of these problems, we're going to take a loop. So here is the loop. All right. Well, are we ready? Nearly. Let's just be careful here. The voltage across this diode, we better call it something plus minus. we'll call that VD1. The voltage across this diode, plus minus, we'll call that VD2. Okay? VD1, VD2. So let's go around the loop. Here we've got 10 going up, plus to minus, dropping, minus VD1, plus to minus, dropping, minus VD2. And then, of course, going from here to here, we're calling that VO, which is what we want to find. That's minus VO, all equals 0. Okay. Now, since we're using the second approximation for each of these diodes, the silicon diode, that's VD1, equals 0.7. The germanium diode, which is VD2, both are in the conducting direction, is 0.3. Okay, we'll put that information into here. Okay, if we do that, we have what? We have 10 minus 0.7, that's VD1, minus VD2, 0.3. Take this to the other side because that's what we want to find. So that goes over to the other side, equals VO. So what do you have? You have 10 minus a 0.7 minus a 0.3. Therefore, this VO then is simply equal to 9 volts. Okay, so VO is equal to 9 volts. All right, a relatively simple problem. Really what we've looked at here are two series circuits. Okay, we'll consider a slightly more involved problem. All right. Okay, let's supposing what we have here now is a voltage source which is 15. Okay? Then we have a resistor which we'll say is a 2K resistor. Then we'll have a diode. Now this will be a silicon diode. Okay? And we'll basically have another resistor sitting here, which we'll say is a 4K resistor. And then we'll have another power supply sitting here, and we'll say that this is a 5 volt power supply. This is now the circuit that we have to deal with. Now, our task is really to find the voltage between this point and this point here, which we'll call VO. That's what we're trying to find. All right? So how do we go about this problem? Well, I think we ought to probably label it first. Okay, so we'll put down current direction. Okay, well, if we look at the current direction here, it is really this way. This diode is indeed going to be a forward biased diode. Okay, so let's call that current, we might as well call it ID. It's the current through the diode, ID. So it's a series circuit, the current is flowing like this. Okay, now having defined the current, let's label some voltages. Okay, of course, plus minus across the diode, that's VD. And then of course current going this way, so we have a plus minus across that resistor, okay, with that polarity. And then of course current flowing in this way, we have a plus minus across that resistor, like so. All right. What we're going to do in this problem then is we're going to try to find what this current ID is. In fact, we need to find that current ID before we can actually find this voltage over here. So how are we going to do that? Well, guess what? We're going to take a loop, okay? And the loop that we're first going to take is really this loop right here, okay? So this is the loop that we're going to take, all right? So there it is, loop 1. All right, let's go around this loop. What have we got? Going from a minus to a plus, we have got 15, okay? Going from a plus to a minus, we've got a minus then. We're dropping in potential here. We've got an ID times that 2K resistor, okay? Plus to a minus, we're dropping, so we've got a minus VD. And then continuing around the loop, we're going from a plus to a minus. We're once again dropping. We've got a minus ID times what? The 4K. All right, not finished yet. We've got this voltage source here. We're going from a minus to a plus. So we would say that's a plus 5 volts, all of that then is actually equal to 0. So this is the loop equation. All right, now we're in a position perhaps to, well, not quite, let's look at VD. We're using the second approximation. All right, so let's put that down. Second approx, okay, second approximation, VD is equal to 0.7, okay? Let's put that information into the above equation. And maybe we can even collect some terms as we do this, okay? So let's see if we can do this at the same time. We've got a 15 here, and then we've got a plus 5 over here, okay? Well, 15 plus a 5, well, that gives me 20, doesn't it? Okay? All right, I've got this term here. It's a minus VD, but VD is 0.7, so that is a minus 0.7, okay? How many IDs do I have? I have a minus 2K ID here, and I have a minus 4K ID here, so that bit plus that bit gives me what? A minus ID 6K, all right? ID 6K. And all of that then is equal to 0. So slight simplification as we've really gone along with this, okay? So 20 minus 0.7, okay, gives me what? A 19.3. If I'd taken that to the other side, that would have been equal to what? ID 6K. So therefore ID then is what? It's really this 19.3 divided by 6K. 19.3 divided by 6K. I'm just dividing both sides by 6K. If you care to work that out, it comes out to approximately 3.2 milliamps. 3.2 milliamps. So, okay, I've found now by taking this loop here, summing the voltages around that loop, I've been able to find this current ID. To find this current ID. All right. Now, what do we want? We want the voltage VO between here and here. Well, really, that voltage is made up of what? It's made up of this guy, and it's made up of this guy here. Now, look, a lot of people get very confused, and a lot of people basically want to do this problem at this stage in their heads, okay? Now, if you're comfortable with doing the problem at this stage in your head, that's fine. But if you're not so comfortable with this material, okay, and you could make a mistake, why not take another loop? There's no reason why you couldn't take, for example, this loop here. Doesn't matter which way round you go, but just sum the voltages around that loop. So therefore, if we do that, we start summing voltages, let's see what happens. Okay, I'll start here. I come to this power source here. I'm going from a plus to a minus. So this is the second loop I'll do now. I'm going from a plus to a minus. What do I call that? I'm dropping in polarity, so I call that a minus 5. Then I come to the resistor. I'm going from a minus to a plus. Okay, so I'm going up. I would call that a plus. What is this voltage here? Well, it is the current through the resistor, which is ID. So let's just write that down. ID times 4K. And now I'm over to here. I'm going from a plus to a minus. I'm dropping. That's a minus VO. And all of that is equal to 0. Okay. A very simple loop. In essence, we don't really have to think about it. We're just taking a loop and we're summing the voltages around that loop. Okay. Now we know what ID is. We have just calculated this ID over here. It's 3.2 milliamps. So we could put that information in over here. And in addition, we could take this VO over to the other side. All right, so let's do that. So that's a minus 5 plus, well, whatever ID is, well, we have worked that out. That's 3.2 milliamps times the 4K, okay, is equal to, having taken that to the other side, is equal to VO. All right, so if we work out this little bit here, what do we have? We have a minus 5 plus 3.2 milliamps times 4K. If you work that out, that's about 12.8 volts, and that is equal to VO. All right, then performing the last bit over here, VO then is equal to 7.8 volts. Okay? So a relatively simple problem, a bit more involved than the previous two, required us basically what? Just to take a loop. And then look, we decided, well, why don't we take a loop here? We don't really have to think about the problem too much by taking another loop over here to determine that VO.